probability generating function is a lot of syllables, so it's shortened to PGF. And there we have a random variable. It has a finite number of non-negative integer values, and we defined its PGF as the polynomial there, where the coefficients are the probabilities, and the power is the corresponding possible value. Now, I should just say that we defined this for a finite number of possible values, but if your random variable has infinitely many non-negative integer values, you can also define its probability generating function. You just have to be careful about convergence, and so in that case you might not define it over the whole line but just over -1 to 1. That is not going to be something we're going to go into. We'll just look at random variables with finitely many values. So what is the purpose of the probability generating function? Well, there are many, but for us it's going to be a way to generate the distribution of a sum of random variables. Let's see how we do that. So here's our definition, and I'm going to rewrite it in a way that will help us recognize this. I'm going to write the s to the k first, and then a times pk, because that is a weighted average, right? You can see something is being weighted by the probabilities. So what's being weighted? Well, we have the generic value k, and then we're applying a function to it. We're weighting that by the probability of getting that k, and we're adding. So yes, it is an expectation. This is the expectation of a nonlinear function of your random variable. And what's the function? We're taking s, which is our point on the real line, we're raising s to the power of the random variable. And so for every s, every point on the real line, what we've got is the expectation of the function s to the x. And this is actually very handy when we extend now to two random variables. So x will have probability generating function gx, and y will have probability generating function gy, and we're going to assume that x and y are independent. Okay, so what we're going to do is look at the PGF, probability generating function of x plus y. So that will be g of x plus y, and at any point s by our new observation, that is the expectation of s to the power x plus y, and that's gotten by applying the observation we just made. So now properties of exponents. The generating function of the sum is the expectation of a product. Now x and y are independent, so a function of x is independent of a function of y, and so s to the x and s to the y are independent random variables, and we proved a little while ago that if random variables are independent, then the expected product is the product of the expectations. And you immediately recognize the two quantities that we've written down. The first one is the generating function of x at s, and the second one is the generating function of y at s. And so, to summarize, the result is that if x and y are independent, then the generating function of the sum is the product of the two generating functions. And this makes it really easy to work with sums of IID random variables. So if you have the sum of a bunch of IID random variables, then what is the generating function of this sum at any point on the number line? Well, if I just had two of them, it would be the generating function of the first one times the generating function of the second one at that same point, which would of course have the same value, and so you'd get a square, but now you have 3, 4, 5 of them. By induction you'll get to the power n. The generating function of the sum is the product of the generating functions, and if they all have the same distribution, then the generating function is the same for all of them. This is handy. Why is it handy? Well, look, the thing we've written down is still a polynomial. Of a pretty high degree, but it's still a polynomial. And you know that the powers are the possible values. And the coefficients are the probabilities. And these, the probabilities, are exactly what we need if we are trying to find the distribution of your sum Sn. And so we have a plan now for generating these probabilities. You can hear me say generate probabilities, so it's a probability generating function. In order to generate the probabilities for the sum Sn, you start with your PGF of x1, and you multiply it by itself. So you raise it to the nth power. That's a polynomial. And when you write that polynomial out longhand, you are looking at the distribution of your sum. So we have a plan that we can execute. Now, algebraically, this is complicated because, multiplying a polynomial by itself and doing that lots of times is quite a lot of work. But we have a computer, and NumPy has polynomial methods. And so, because we have computation, we can very quickly compute exact distributions of sums of IID random variables using generating functions.